Yeah, it's about program extraction and the proof assistant Minlog, and then I implemented some number theory in it. First of all, I want to speak about program extraction. For this, we need a computable relevant formulas, and I want to give you a short overview. It's part of a definition, but not a full definition. A formula is computational relevant if actually the elementary computational relevance consists only, in our case, only of these two formulas. You have the disjunction and the existence quantifier. Because these two, maybe you already know this, but these two are the computational relevant formulas because you always need a witness. In the first case of a disjunction, you need a witness if here A or B holds. And for the existence quantifier, you need a witness for which term A of this term holds. And in our case, these two are enough. Then if you have not elementary formulas, but formulas with some logical symbols between, then these rules here apply. A implies B is computationally relevant if B is. That conjunction is quite trivial if one of them are computationally relevant, and the all quantifier is also just computationally relevant if the kernel is computationally relevant. Then there are formulas which are not computationally relevant. For our case, it's important to note that some negative formula is not computationally relevant, that equalities are not computationally relevant. This is important. And Boolean terms, actually, a Boolean term is interpreted as a equality just by this Boolean term is equal to true. So you have, for example, also this Boolean version of the disjunction and the conjunction, which are just defined as usual. Maybe you know it from the beginner lections. And also very important is that a bounded existence quantifier is also it can be interpreted as a Boolean term and is therefore not computationally relevant, in contrast to to an unbounded existence quantifier. You can imagine this here. This is not computationally relevant because you already get the information to compute a witness by just going through all possibilities here. Whereas the unbounded existence quantifier, you cannot test infinitely many possibilities, but here you have finitely many. Okay, just for the intuition, hopefully you have maybe already seen this. And out of computational relevant formulas, we now want to get an extracted term or a program from a proof. And there is this program extraction, which is part of Minlog. And I will give you here a compact overview because it's also a quite nice idea. First of all, you have such a computationally relevant formula. And from this computationally relevant formulas, you can define the type of this formula, which and also a realizer predicate. I will not go in detail of this definition. However, this is done over recursion over A, or over the how A is built. For example, if you have an existence quantifier of a elementary formula, then the type of this formula would be just the type of the quantified variable. If you have an all quantifier, then actually this is a bit more complicated, but in general, if you have an all quantifier over an arbitrary variable, then this all quantifier is just left out and you just take the kernel. But often the all quantified variable has also some properties, and these properties then will contribute to the type or the realizer predicate. Yes?
For existential, I would expect a pair or something about the existential difference, and then
Yeah, actually, you're right. What I thought here is if you have an elementary formula, but this is what you said is more the general case. So, thank you. Okay. Out of type and realizer predicate, we get this by looking at the formulas. But if we now have a proof, which I here call M, then we can construct the extracted term ET of M, which is a term of type A. And we do this by induction over the formal proof of M. And this is where we really need proof assistance, in particular Minlog. Because this here is extremely complex for humans to do. Okay, and yeah, as you might now think, and it's correct that this extracted term is indeed a realizer, which says it fulfills the realizer predicate. And this is the so-called soundness theorem of program extraction, which just say if you have a formula and a proof of this formula which do not have this realizer predicate already inside, then the extracted term fulfills the realizer predicate of the formula. Yeah. And yeah, as I said, it's very important that here, or it's not feasible for humans to in detail compute the extracted term. So actually, it's we need here a proof assistant, and this construction of the extracted term is implemented in Minlog, and that's why I have used Minlog here. Okay, for this, I first want to give you a short overview about Minlog. Here are a few details. It's worth notice that this the development of Minlog goes back to the 1990s, so it's not that young actually, and it was done by mostly by Helmut Spichtenberg at the Ludwig Maximilians University in Munich. Then Minlog is written in the program language Scheme and based on the theory of computational formulas. Theory of computational formulas is a type theory and has a model which is built on, as the name says, partial continuous functional information system. It's not important so much. I don't just want to say these words. If you want to look them up, they are quite interesting. So the theory about this, and you should know that there is indeed a intended model of the theory of computational formulas. This is also quite interesting. Minlog uses a tactic script, and okay, the tactic script is also written in Scheme, so it's Scheme language. However, it is meant to be closely to a traditional textbook language. Of course, this is not 100% possible, but at least some words and some phrases are taken from this textbook languages. Okay. Don't matter. Then also quite interesting. We have this formal program extraction. We have other proof interpretations which can be done in Minlog. And a nice feature of Minlog, even if it's written in Scheme, the terms and programs can be translated to Haskell terms, which is, by the way, was done by Frederick. And the thing is that usually Minlog was used for constructive analysis mostly, but my novelty here is that I have now implemented number theory in Minlog and used the program extraction. I will now shortly outline for the remaining 5 minutes about this implementation. First of all, it is quite interesting how if you do some implementations in a proof assistant, you always have some choices to do because you have to be very precise. And it's something like, I said always, it's something like quantum mechanic, whereas the more precise you measure, or the more precise you are, you more have to collapse in quantum mechanics the wave function, the probability function, and here you more has to precise the details. The details collapse. There are, for example, two possibilities to define natural numbers. First is actually you know both, but you have zero and successor. And the other is by positive binary numbers. And I did in particular both of them in Minlog, and you can even go through them, to both of them. And why have I done this? The proofs are much more simpler by using the natural numbers, but the extracted terms are much more efficient by using positive binaries. And we will, for example, see this in the greatest common divisor algorithm. For example, this here is done this is the normal Euclidean algorithm done for natural numbers, so for zero and successor. However, if you have the positive binary numbers, which are here, you have the zero successor and the one successor, then you can be much more efficient but okay, here you have more cases. So actually, if you use them in each step here, at least one digit will go away. But therefore, the definition here is more complicated. This is what goes through all of them. Let's I see how many time do I have left. 3 minutes. Yeah, I see also. I think that this should be enough. I give you here an example what I have implemented. Here you also see the Franziskus identity, which is formulated as if you have two integers, then the greatest common divisor of these integers is a linear combination of these integers. However, this is also something when you implement this, you have to really get the type here of integers. And actually, what I found out is that there is no point in using integers. You just can use natural numbers and make a case distinction here. Here again, you have the natural numbers with a successor function, and you always put the negative term or just to the other side. So therefore, you have here this case disjunction. However, for positive numbers, we don't have the zero available because they are positive binary numbers. And there are reasons why you don't want the zero in this case. And in this case, if you formulate it for positive binary numbers, you need indeed 4 case distinctions. The first 2 here just saying if one of them is 0. If one of them is 0, then the greatest common divisor is a multiple, or is exactly one of them, a multiple, which means it's one of them. And then you have that the other one is just a divisor of the greater one. Therefore, you have here the 4 possibilities. And as you see here, it's again, for positive binary numbers, the theorem looks quite different, quite more complex. However, the extracted term is simpler. So for the last thing, I want to show you maybe the fundamental theorem of arithmetic. I think this is a good ending point. Fundamental theorem of arithmetic. There's the existence part. The existence part just says there is for each positive number, in this case, there is a prime factorization, this Pm of Ps. This Ps here, that's the point here. This Ps is just a sequence of positive binary numbers. And then the product over this Ps up to M is then P. And here it's also, this is something also quite interesting that really you take in Minlog, you take a sequence here. In Acta, you would not take a sequence because here you have dependent types. And in Acta, you would really take this M here as a as a parameter of this type. This is also quite interesting that in Minlog you really do it with sequences. Yeah, because of time reasons, I will just show you now the formulation of the uniqueness. And here for the uniqueness, you see you assume you already have a prime factorization, and which then the number of factors is equal, and you get some f and g. And here again, you have some permutations. This f and g should be permutations and the inverse of each other. And again, here it's a permutation of the natural numbers and not on on some finite set, which is also comes from Minlog and is due to the fact that there is no dependent types. Okay, I think I will stop here. There, maybe just showing there's also the Fermat factorization, which I did as application, which is a possibility to factorize some numbers in a slightly more efficient way, depending how this number is built. And yeah, I think I will stop here. Thank you for attention.